welcome to my presentation on nonlinear filtering with Brenier Optimal Transport Maps. This work is a joint work with Jenny, Bamdad, and Amir Hussain. Let me start from the problem setup, where if we have a hidden random variable x and some absorbed random variable y, and we want to answer the question of what's the conditional probability distribution of x giving y, which is known as the posterior distribution. Now Bayes' law give us this simple formula for if we have the prior distribution px and the likelihood distribution by given x. We can write this simple expression for the posterior distribution px giving y. This expression is simple, however is difficult to implement numerically. Let me show how with a simple example here. Now if x is distributed as a standard Gaussian and y is some realization of x squared plus some standard Gaussian noise controlled by this epsilon to control the noise level. And we want to answer the question of what's the distribution of x giving y equal 1 for this example. Now using a method like importance sampling, we start by we start by generating some particles as we see here as the green dots, and the orange bars represent the histogram of these particles from the prior distribution px. And we use these particles with the likelihood model we have to update the weights for each of the particle, and use this weighted distribution of the particle to represent the posterior distribution px giving y equal 1 for this example here. Now as the noise level goes to 0, gets smaller, we start seeing this degenerate likelihood distribution, and we end up having all particles have weight 0 except one of the particles gets all the weights, which is 1 here, which is 1, and when we get the weighted distribution of the particles, we end up having only one of the modes, and this is known as the mode collapse, which is the main reason behind the cursive dimensionality of importance sampling based particle filters. Now from conditioning, from a transport perspective, the question is slightly different. Now if we have some particles that represent samples from the prior distribution px, and we want to generate a new set of particles that represent the posterior distribution px given y, we want to learn this map. Now the question becomes how to learn how to numerically find the map T in a general setting. Let me show how we do this with the same example we saw before. Now we start from the prior distribution px with these particles, but instead of going to the posterior distribution px giving y, we generate samples from the joint distribution px giving pxy, and taking these particles from the joint coupling, we generate the independent coupling by shuffling x, and after that we learn a map T that moves these particles from the independent couple px py to the joint coupling pxy, and this is how the new transported particles from the independent couple to will show up here as the green dots here. Now we use this map T with the fixed observation y for this example is equal 1, and we use the particles from the prior distribution px to learn to move them to the posterior distribution px giving y equal 1. As we see here, the particles will represent the posterior distribution, and as we get the likelihood, the degenerate likelihood case, the importance sampling failed to represent both modes. However, the transport method was able to capture both of the modes. Now, from going back to Bayes' law, from a transport perspective, we present the posterior distribution as the map T that takes the true observed Y and pushes forward the prior distribution to the posterior distribution without the need of the likelihood model. Now, this map T is a solution for this max-min problem, where this max-min problem has some nice features. One is it's a sample-based algorithm where only it requires samples from the joint distribution, and we can use stochastic optimization to solve for these f and t functions, and we can use neural networks to represent the class of functions f and t. And these features will allow us to overcome some challenges like the degenerate likelihood case we saw earlier, and being able to represent multimodal distributions and solving high-dimensional problems. Thank you for listening, and here's more details about our poster session in ICML. Thank you.